Have you ever wondered how a network can be lightning fast without giving up on security or decentralization? Well, today we're diving into Kaspa's pretty brilliant answer, a concept they call virtual parents. It's a really clever solution to one of the biggest puzzles in crypto. So let's get right into it.
Okay, let's start with this big question right here. Picture this. You have a system where tons of people can all add to the story at the exact same time. How on earth do you decide which version is the real one? It's kind of like trying to write a book with 1,000 authors all typing at once. That's the core problem Kaspa was designed to solve from the ground up.
Now this challenge actually has a name. It's the problem of having too many tips. You can think of it like having way too many cooks in the kitchen, right? Everyone's got a different idea for the final recipe, and it can just lead to absolute chaos.
So, take a look here. On the left, that's your traditional blockchain. It's a single, neat and tidy chain where everyone just adds their block to the very end. Super simple. But then, on the right, you've got Kaspa's BlockDAG. It's much more like a tangled web, with lots of different tips or endpoints all existing at the same time. This structure is what makes Kaspa so incredibly fast. But, as you can probably guess, it also creates some pretty big challenges.
So what are these headaches exactly? Well, for one, if you're a miner, which block are you supposed to build on? With so many tips, the network security gets spread way too thin. Second, trying to process all those branching paths at once gets really expensive computationally and fast, and that can make it just too costly for a regular person to run the node. And third, it's just harder to be sure that past transactions are truly locked in, set in stone, and can't be messed with.
So how do you get all the amazing speed of a BlockDAG without all that chaos? Well, Kaspa's answer is a really elegant concept called virtual parents.
Okay, so what in the world are virtual parents? In simple terms, they're a small, very carefully chosen set of blocks that get picked from that big, complex web. These blocks then become the parents of a new virtual block. Now, this isn't a real block you can see on the chain, but it acts like a single, trustworthy point of agreement that the entire network can look to.
This committee analogy is honestly the perfect way to think about it. Instead of every single block shouting for attention, the network is constantly electing a small group of the most important ones. This committee then makes a single, clear decision, and everyone else just follows their lead. It's how Kaspa brings order to all of that potential chaos.
But how is this committee even chosen? I mean, you can't just pick blocks at random, right? That would be a security nightmare. No, there's a very specific and very rigorous process behind it all, and that's the selection algorithm. Let's take a look at how it works.
The whole process basically has two main steps. First, the algorithm finds something called the sink. This is the block that has the most computational work backing it up, what Kaspa calls blue work, which makes it the most secure candidate. That sink becomes the main virtual parent. Then, the algorithm adds a few more parents based on a set of really strict rules, just to keep the network diverse and running nice and smooth.
And these rules, well, this is the secret sauce. Each one has a very specific job. The merge set size limit, for instance, keeps things manageable for everyday people running nodes. The parent count limit stops the processing power from getting out of hand. And those other two, bounded merge depth and finality depth, they're basically security guards, making sure nobody can go back and mess with old transactions. So it's not just one rule, it's a whole system of checks and balances working together.
Okay, so we have this really elegant system for picking a committee of blocks. But what does the network actually do with them? Let's look at how these virtual parents become the very foundation for how the network operates.
For the miners, this is a total game changer. Instead of having to guess which of the dozens of tips they should build on, they get one single clear target, that virtual block created by the virtual parents. This focuses the entire network security, all that hash power, onto a single point, even while new blocks are being created in parallel all over the place.
Second, it's a huge deal for the network's ledger. The official record of who owns what, the UTXO set. Well, that's calculated based on these virtual parents. The network takes the state of that main sync block and then just quickly adds in the transactions from the other parents. This means the ledger can be updated unbelievably fast.
And finally, for all the nodes that make up the network, virtual parents act as a simple, really elegant synchronization point. When two nodes want to check if they're on the same page, they just have to compare their set of virtual parents. It's a super lightweight way to confirm they share the same view of the network, with almost no delay.
So we've seen how it all works under the hood. But let's get to the most important part. Why does any of this actually matter? What does all this clever engineering mean for you in the real world? The first massive impact is just raw performance. Virtual parents let Kaspa process a huge number of blocks in parallel, which means you get incredibly high throughput. But, and this is the crucial part, it does all this while keeping the processing and memory needs for nodes really low. This means more people can participate, and that is the absolute bedrock of decentralization.
Second is something called network convergence. This system makes sure that a globally distributed, totally decentralized network can agree on a single version of the truth and agree on it fast. Reaching that consensus quickly without any central boss telling everyone what to do, well, that's kind of the holy grail for a system like this.
And finally, we've got robust security. That multi-layered system of rules we looked at, it isn't just for performance, it's a fortress. It's designed to make it practically impossible for anyone to manipulate the selection process, which prevents attacks and protects the integrity of your transaction history, even when things are moving at incredible speeds.
So if you're going to take away just a few key things, here they are. First, virtual parents are dynamic. They're not fixed, they adapt to the network in real time. Second, the whole system is optimized for performance, keeping things lean and accessible. Third, its security is multi-layered, using a whole web of rules. Fourth, they are the literal foundation for everything from mining to syncing. And finally, the design is configurable, which means it can evolve as the network grows.
And that leaves us with one last big thought. For decades, the blockchain world has been wrestling with this classic trade-off, the trilemma, forcing projects to choose between speed, security, and decentralization. But if a system like virtual parents really does let a network achieve all three at once, well, what kind of new possibilities does that unlock for the future? That's definitely something to think about. Thanks for joining this explainer.